Hello, YouTube community and Khan Academy. My name is Theo. I'm an actuarial science major and have been teaching math, finance, and statistics classes for the last 3 years. Today I'm going to run over everything you need to earn credit on the AP Statistics College Entrance Exam. Mainly focusing on what I hear is the most difficult section for any students, and that is probabilities. First off, what is probability? Probability is the chance of anything happening. It's a guess. There's a 30% chance it rains tomorrow. What does that actually mean? It's either going to rain or it's not. But we guess. There's a 30% chance it might happen. So, a probability can be represented as a decimal between 0 to 1. A 30% chance is 0.3. When you're looking at probability of problems on this exam, you're going to have your situations are either going to fall into one of two categories. Either discrete or continuous. This is the first question you have to ask yourself every time you're looking at a probability problem is, can I count it? Discrete things talk about things you can count on one finger. If I'm rolling a dice, I'm rolling a 1, 2, 3, 4, 5, or 6. If I'm flipping a coin, I'm landing either heads or tails. So think about things you can count. Discrete is countable. So in the discrete category, you're going to have the uniform, which is like coins and dice. They have even chances of every possibility in them happening. I have even chances 50-50 of flipping a heads or tails, or I have a 1/6 chance of rolling any number on a dice. The other distribution in that you're going to need is the binomial. Think about shooting free throws. I'm not very good from the free throw line. Maybe I have a 1 in 4 chance. I have a 25% chance of making one free throw, and I'm shooting 10 of them. So this distribution will give you the probabilities of making any number of free throws out of that total number you get. You're going to be given an n and a probability of making that many out of 10. Think 25% out of 10 shots. So, what if you can't count it? What if I can't hit exactly, 1, 2, or 3 free throws? You have these continuous categories. Their favorite one to talk about, and it's guaranteed to be at least half of your AP statistics test, is the normal curve. Everyone loves that nice bell-shaped curve centered around the mean, and you're also going to be given a standard deviation to shape that curve. That'll be in a whole separate video. That's a big topic. I would be very familiar with normal curves. You could also have the uniform. Same as over here, except for now it's continuous. There's in-between numbers. The last thing you could possibly have in the continuous category for this exam is going to be chi-squared, but that'll be more for hypothesis testing in the end of the year. Several videos to come on hypothesis testing, but always remember, you're always getting area out of a chunk of a curve. This normal curve has an area of 1. 100% of the things that are going to happen between there and there. So you're going to get chunks out of that normal curve, and that'll be probabilities between those regions. The last and most tricky part, the one I get the most frequent amount of questions on from students, is what happens when they ask a probability problem but don't give me probabilities to work with? What if they just give me a table with counts? And that's going to happen. That's going to happen on your test. Almost guaranteed. So I pulled one off, an old exam, literally used exactly the same numbers. Let's look at that. What if they just give you counts? Ooh, that marker. Yeah, go ahead. Let's see if this marker treats me better. This one they're talking about the number of people that are in each political party, given you're a man or a woman. So you have the men up here, the woman down here, and you're either in political party A, B, or C. Oh, you're killing me. So, they tell me that there's 60 men in party A. There's 28 women in party A. There's 120 men in party B. There's 124 women in party B. 120 men in party C, and 48 men in party C. And this comes out to, trust my math, this comes out to 500 total people in all of these. So they're going to ask you problems like, what's the probability of being a man? This probability notation, P parentheses. So what's the probability of being a man? That's a fair question they can ask on the table. But keep in mind, even if they don't give you decimal numbers in here, you can convert them just as easily to decimal numbers yourself. 60 divided by 500 is a probability in and of itself. It's 12%. I can do that for the rest of the table. 28 divided by 500 is 5.6%. 124 divided by 500 is 24.8%. 120 and 120 divided by 500, each of those are 24%, 24%, and 48 divided by 500 is 0.096. So the probability of being a man is just all these boxes divided by the total box. You got 60 in party A, 120 in party B, and 120 in party C. So that's 300 out of the 500 total people. So you have 300 men out of 500 men and women. The probability of being a man is 60%, which is 0.6. Either of those are an acceptable answer to what's the probability of being a man given this table. Just like I totaled it here, and this is 300, you can total each of these on the side, no problem. There's 300, that means that's 200. This is 88, this is 244, this is 168. And I can make decimals. This is 6%, so this is 0.6, that would have to be 0.4. I can do that for this too. This is 0.176, this is 0.488, and this is 0.336. The second thing they're going to ask you about a table like this is something called conditional probabilities, or given statements. And they assign big math words to very easy kind of questions. They're going to say, what's the probability, these markers are killing me. Say, what's the probability of being in party A given, it's given notation, a vertical line, given you're a man. So what's the probability? You already know you're in the man category. So out of all the men, what's the probability you pick somebody out of this table that's in party A? So instead of having everyone that you're talking about, probability man out of everyone, you already know you're only in the man category. So instead of 500, you're now only in 300 in the denominator. So now you're only looking at the denominator is 300. These markers are killing me. And now you have all the people in party A that are men in the numerator, because you already know you're up here, so you block out the bottom part. You're not even talking about the women category. So now you have 60 out of 300. That's 0.2, which is 20%. Those are both acceptable answers for what the probability of being in party A given you're a man is 2.2 or 20% are both full credit answers for that question. The last thing they can ask you in this whole one, in a whole table like this, is a concept called independence. Now the event of flipping a coin is independent. If I flip one heads, it doesn't affect the chances of me flipping a heads on the next try. If I have a 50% chance of flipping a heads, I have a 0.5 times 0.5, I have a 0.25 or 25% chance of flipping two heads in a row because they're independent events. So, by that logic, if the events of being a man or a woman, or the events of being in political party A, B, or C are independent, we should be able to multiply these probabilities of being either in party A or being a man or woman, And we should be able to multiply them together and get the probabilities in here. If they match, if these numbers, these probabilities, 0.176 times 0.6 equals the actual count that we observed, 0.12, for all 6 boxes, then the events are independent. Knowing if you're a man or a woman or party A, B, or C doesn't affect the chances of being the other. So we can test that very easily. They're going to ask you a question like, are gender and political party independent? Easy enough question. You can just look at the counts. So we're looking at the inequality. There's the probability, and I'm going to look at this box. You can pick any box arbitrarily. I'm going to pick that box and that box. And if they are in fact independent, then that times that should equal that probability. So we're looking at the inequality. Does the probability of being in B times the probability of being in a woman equal the probability of being in party B and being a woman? If it's equal, for all the boxes, it's independent. But if it's not equal, then we have evidence that the events, in fact, are dependent on each other. So the probability of being in party B, we found is 0.488, times the probability of being a woman in this was 200 out of 500, which is 40%. Does that, in fact, equal the probability of being a woman in party B, which is this box, which is 0.248. If I do my math correctly, this comes out to 0.1952, which does not equal 0.248. Now, because of that inequality, we can stop. And we do, in fact, have evidence to say that the events are not independent. How you handle a table like that. Thank you guys for watching. Please subscribe for new videos or leave a comment. Anything you guys are tripped up on or want more info about. More videos to come. Good luck on the exam, guys. Thank you for watching.